Okay, so it's just a bit of an equilibrium overview, how to tackle questions that are asking you about shifts in equilibrium and about stresses that are being applied. Okay, so the reaction that we're going to look at is actually for a process called the Haber process, which is the industrial production of ammonia. And I chose this reaction because we've got an unequal number of moles in reactants versus products, and we've also got an exothermic forward reaction, which means we can talk about all the different stresses that can be applied to a system. Okay, so first thing to remember is that a negative energy per mole tells us that that forward reaction is exothermic. So in the forward direction, we're going to get a release of heat, and in the reverse direction, we're going to get an absorption of heat. Okay, so recognizing that forward is exo and reverse is endo. So if we talk about stresses that can be applied to a system, we know that Le Chatelier's principle tells us that this system, when it is stressed, is going to act to counteract that stress by favouring a particular reaction. So it's kind of the idea of opposites. Everything happens in opposites. So because the forward reaction is exothermic, when the forward reaction is being favoured, the temperature of the surroundings will increase. When the reverse reaction is being favoured, the temperature of the surroundings will decrease. So if our stress is relating to temperature, if in this system we increase the temperature of the system, so that might mean that the industrial plant has increased the temperature of the surroundings to try and force this system to do something. If you increase the temperature of a reaction that is exothermic in the forward direction, it's going to favour the endothermic reaction, which in this case is the reverse direction. And the outcome for that would be an increase in reactants. So I've talked a little bit in class about how you set out these sorts of questions. So what you're doing is you're identifying what the stress is. You're identifying how the system will counteract that stress. You're identifying which reaction is favoured as a response to the counteract of that stress, and then you're identifying what the outcome is. Okay, and it's really important that you follow that sequence when you're dealing with questions that are 3 or 4 marks in response to an equilibrium question. Okay, so what's the stress? How is the system going to counteract it? What reaction is then going to be favoured? And then basically what's the outcome? So this part is often, it can sometimes be a colour. It can be asking you what happens to a particular species within the reaction. It can be lots of different things, just depends on the question that's posed. Okay, if we look at the opposite, if temperature is decreased in this particular system, then it's going to favour the exothermic reaction in an attempt to increase the temperature that has just been decreased. That means that we're going to favour the forward reaction, and that is going to lead to either a decrease in reactants or an increase in products. Okay, so we're going to get more ammonia. The second stress that's talked about quite a lot is pressure. Now, when we talk about pressure in a system, we need to consider the molar ratio of our system. So in this system, I've got 1 mole of N2 and I've got 3 moles of hydrogen. So I have 4 moles of gases in the reactant side. I have 2 moles of ammonia. So I have 2 moles of gases in our product side. So if I increase the pressure of the system, now increasing pressure of the system actually means that you have decreased the volume. So remembering in equilibrium, we're talking about a closed system. So if you can imagine all of the gas molecules in this much space, If you decrease the volume, so you suddenly give them half as much space as what they first had, so all of our little molecules are now stuck down the bottom here, there's an increase in pressure in that system, okay? Because pressure is determined by these molecules bouncing into the outside of the container. So when you increase the pressure by decreasing the volume, this is our stress. Both of those two things are considered a stress because they are the same thing. What's going to happen? The system wants to try and decrease the pressure that has just been increased. And all it can do is try and decrease the number of molecules that are within that space. So it's going to favour the side of the reaction that has less gaseous molecules. So we're favouring less gas moles. Now in this reaction, less gas moles is favouring our forward reaction, which means we're going to increase the amount of ammonia. Okay, so if the stress is an increase in pressure or a decrease in volume, how we counteract that stress is by favouring less gas molecules. In this case, we're favouring the forward, and our outcome is an increase in ammonia. Okay, what happens in the opposite? If we decrease pressure, decreasing pressure means that we've increased the volume. Okay, we've suddenly given those gases excuse me, much more space to play around in, which means the collisions with the wall are happening much less, which essentially is a decrease in pressure. What we want to do when we do a decrease in pressure is we want to favour more gas molecules so that we can increase the pressure again. And in this reaction, that means that we're going to favour the reverse, which means that we're going to get a decrease in ammonia. Okay, so temperature and pressure are our two really big stresses that are often talked about in an equilibrium system. The other thing is just changes in concentration. Okay, so they might be stating that we increase the concentration of nitrogen, that's going to cause the forward reaction to be favoured. We remove ammonia, it's going to cause the forward reaction to be favoured. We increase the concentration of H2, it's going to cause the forward reaction to be favoured. If we increase the concentration of ammonia, we're going to go backwards. So concentration changes when you're talking about species that exist within the equation are really easy to deal with. Concentration changes when the species is not in the reaction, so you've got to think about a secondary reaction, is a little bit harder, and I'll do a couple of examples in the next video. So hope that helped, Chels.